Do you think everyone's here? Okay. Well, hello, everybody. I hope not too many of you are suffering from post-traumatic lunch syndrome. I know that I am. Well, my name is Tom Ayres. I'm here at the University of Colorado. I'm a research professor. I would say probably 5% professor and 95% research. My main area of activity is in solar stellar research. And so I come to you today to talk about that particular subject. And I should mention that the lecture following mine, oh, come on, is being delivered by Professor Baker. And I have to tell you, he is a hard act to follow. In fact, it's going to be a very difficult act to follow if I can't get this going again. And so I'm glad I'm going first. Okay, so today I'm going to talk about solar stellar activity and solar stellar winds. This is a vast, huge topic, so I'm going to have to really condense it quite a bit. Here's an outline. I'll start by describing, by trying to provide a definition of activity. I'll talk about phenomenological properties of activity across the HR diagram, how we observe activity, and a little bit about stellar winds and how they fit into this whole picture. And finally, I'll talk about stellar cycles at the end if I can get there. There will be two kind of main themes that pervade this talk and are of interest to the summer school. And that is, what can unresolved stellar activity, or observations of other stars, what can that tell us about the activity on our own sun, particularly in the past and in the future, where we only have the contemporary sun, we observe it in real time. But really, what happened back in the dim, dark, distant days in the early parts of the solar system, and what's going to happen in the far distant future. And the other sort of subtext in this presentation is this question, is the sun really a normal star? And there have been many kind of complaints in the past that the sun is somehow unusual among the broad mix of stars we can observe in the universe. And so I want to set you straight on that topic as well. Okay, well, what is stellar activity? In my way of thinking, trying to describe activity is like trying to describe beauty. It means different things to different people. It's hard to describe, but most people kind of recognize it when they see it. So I'm going to try to give you some definitions of activity, and we'll see how they work. The first one that I've seen, actually I think I pulled this off of Wikipedia, involves solar phenomena that occur on timescales shorter than the thermal timescale. So now, I should say, please ask questions. Because if you don't ask me questions, I'm going to ask you questions. And so, yes, sir. No. That's my job. So I'm going to ask you, what is the thermal timescale, and why is it important? Yeah, see? No, you were way ahead of the curve. So anyone know what the thermal timescale and stellar evolution is? And why it's 100,000 years? Oh, that's the hard part. Okay, well, the thermal timescale, think of the sun as a giant capacitor that's storing a huge amount of energy. That energy, of course, is being generated in the core, and it's being radiated from the surface. But in fact, the sun is like a giant capacitor. It stores a huge amount of energy, and that leak of luminosity from the surface is actually a tiny fraction of the energy that's stored inside the sun. And you can sit down and figure it out. It's basically an NKT thing. Well, we know what K is, I hope. And the temperature inside, the average temperature inside the sun is about 1 million degrees. And there are a lot of N in the sun. The number of protons in the sun is ginormous. And so you multiply all those things together, and you get a certain number of ergs. It's a huge number of ergs that the sun stores in its vast thermal reservoir. Then you divide that by the luminosity of the sun, which is something we measure, we know, ergs per second, and then you get a time scale. And that time scale turns out to be 100,000 years. Now, the implication of this time scale is that if you could, maybe the Army Corps of Engineers could turn off the nuclear furnace on the inside of the sun today, we really wouldn't know about that for about 100,000 years. Because the sun has enough energy, internal energy, to shine for roughly 100,000 years without changing appreciably. And so this is kind of the somewhat related to the nuclear evolution timescale of the sun. So it's a very, very long timescale. And this has been used by some to describe the timescale of relevance for activity. So anything that happens faster than this should be considered solar stellar activity. I'm not really very comfortable with this definition because there are a lot of things that happen on the sun on very fast timescales that have nothing to do with the activity that I'm going to be talking about. There are things that are peripherally related. So the things like thermal convection, which occur in timescales of hours and minutes on the sun. There are sound waves, internal sound waves, helioseismic sound waves that have sort of minute timescales, and that sort of thing. So I think this is a very unsatisfying definition or potential definition of activity. What I like better is the idea that activity is something that's associated with evolution of the magnetic field. Because the magnetic field in the solar surface evolves on a wide range of timescales. And from very, very fast to years, decades, centuries, and millennia. So I'm going to adopt as a working definition that activity is associated with changes in the solar magnetic field. And here's an example of some changing magnetic fields on the sun, as observed by the Japanese Hinode satellite in their solar optical telescope. And what you just saw was emerging flux, the magnetic field of positive and negative polarity emerging from the subsurface layers of the sun into the visible surface layers. We're seeing here the radial field, and you can imagine all these field lines that extend up into the corona and energize the plasma there. But you see these very fast timescale changes in the solar surface that occur because of these magnetic fields. Now, if there were no magnetic fields on the sun, what are the basic phenomena that you would see? And I'm going to ask this gentleman over here with the beard who was so precocious at the beginning. So if the sun had no magnetic field, what would be the dominant phenomenon you would see on the solar surface? Yeah, it would be the granular convection that we're all familiar with when we look at white light pictures of the sun. But the magnetic field complexifies all this and makes the sun a lot more interesting. Oh, and I guess at this point, I should ask the question, maybe I'll ask you, since you look like quite a bright person. So what's the difference between a colloquium, the sort of thing that I usually give, and a lecture, the sort of thing that Dr. Baker usually gives? That's a good answer. But the way I would answer it is, in a colloquium you have younger students that ask. I'm sorry. In a lecture you have younger students that ask questions, but in a colloquium you have old farts that just sit there and sleep. Is that what you said? No, I'm sorry. That's not what you said. Okay. So the way I would answer that question is to say that a lecture is all business, and it's facts, facts, facts. It's all business. There cannot be any fun. Okay, so I just want you to keep that in mind. Well, maybe a little bit. I don't know. Okay, so I can't resist introducing at this point Jeremy Drake's ladder of cosmic sexiness to really put all of this into a context. So here we have the cosmic sexiness ladder, with cosmology and quasars, right at the top, and stars and the sun at the bottom. And you see, here's the arrow of information, and here's the arrow of sexiness. So you see, I'm going to talk about stars. That's a lot better than the sun here. It's right at the bottom. We know a lot about the sun. Now, what's actually missing from this diagram? And if Fran were here, planets of our solar system. They're down off the bottom of the chart. We've actually been to one of them. Well, the moon. It's not really a planet, but it might as well be. And we sent our robots to the other ones, so we know a lot about the planets, and we know a huge amount about the sun, and we know almost nothing. Well, look, planet hunting is way up here, and Fran will tell you those exoplanets, they're no good, and I somewhat agree. But there's a lot of mystery up here, and I know a lot of students tend to be attracted to those areas. But you'll notice that there are a lot of us folks that are working down here in solar physics and stellar physics, and there's a very good reason for that. Oh, I should point out that there's this great quote that's attributed to Bob Layton, one of the pioneers of oscillation studies. The sun, if the sun did not have a magnetic field, it would be as uninteresting as most astronomers think it to be. Those are the astronomers on the dark side, as we say. But the reality of it is that the sun is a resolved object, and you can learn a huge amount about the physical processes that occur in the sun because you can actually study them. Whereas in these very remote and distant objects, they're so distant that we can't resolve them. And they're so faint in many cases, even though they're intrinsically quite bright, that the amount of information we can derive from photometry and spectroscopy is quite limited. So the sun is a huge resource for understanding cosmic physics. And above and beyond that, of course, and there are quite a lot of folks here in Boulder that make their whole livelihood on this other aspect. Well, the sun is hugely important. To the human race and to, the heliosphere in general. And so the other point here is that a lot of the stuff we can learn about in great detail on the solar surface, and particularly the sorts of phenomena that are associated with the magnetic field, can be reapplied back to some of these more distant objects that are being controlled by the same forces, but at a much grander scale. So we have a lot of feedback that can be provided to those other areas. So this is just the obligatory slide showing the poor Earth down here being pummeled by a coronal mass ejection from the sun. So what's wrong with this picture? Well, no, it says right here. It says a scale to approximately the same relative size. Thank you. I really appreciate it. I was involved many years ago with one of my students, Jeff Bennett, in creating a scale model solar system on the CU campus. If you go down by the planetarium, you'll see this structure. And Jeff was the sort of the guiding light in this whole endeavor. And he had 4 undergraduates. He was a grad student at the time. He had 4 undergraduates working with him. And they laid out this scale model solar system with, they used a grapefruit for the sun and ballpoint pen tip for the Earth. And they laid them out, and I was absolutely astounded. I'm a professional astronomer, and I know this stuff. But when you actually see how big the scales of the solar system are and how tiny all the objects are, it's really, it's quite dramatic. Anyway, so I hate these pictures because it just gives you totally the wrong impression. Okay, well. So here's a fundamental question that we stellar people have to ask ourselves. And that is, when you have these beautifully resolved time-lapse movies of the sun, why would you even, why go there? And this isn't even as good as it gets. I mean, these are old. These are actually poor reproductions of old SOHO EIT frames. Now we have AIA as Carl Schreiber will show us hours and hours of extremely high-resolution, beautiful pictures of the sun. And, you know, we get this stuff 24/7. You know, you're lucky if you can get a single Hubble observation of a star. And it's a really tough thing. So why do we even bother with the stars? Yeah, I know. And this is something that Carl has worked on quite a lot. Yeah, it's not the relative size. Sorry about that. It's not the relative distance either. Yeah. Oh, well, so here's a good question for you. I'm putting on my scale model solar system hat now. Is Quinn here? Oh, Quinn's in the back. Okay. You can probably answer this. Okay, so if I'm a 14-centimeter ball representing the sun, how far away would the Earth be? Yeah, the scale is 1 to 10 to the 10th, just as a quick clue. That's about right, yeah, it's about 15 meters. Okay, now, the real question, that was the warm-up. The real question is, where would the nearest star be? And think, I mean, just name me a city. Yeah, from here. New York, yeah, New York is good. New York is about right. It's actually the Panama Canal. But that's about the same. New York's a little closer than the Panama Canal, but it's about 4,000 kilometers away. So 4,000 kilometers away, there would be the next nearest star, which is about the size of a grape, Proxima Centauri, a little red star about the size of a grape. And then not too far beyond that, another 100 kilometers, would be an orange and another grapefruit. These are the Alpha Centauri stars. And they'd be separated by, now, 80 meters or so. And so that's bigger than this room. Anyways, I'll get to those guys later. So why do we study the stars? Well, I mean, the answer is somewhat obvious, and that is that we only have one sun, and we're seeing it in real time. And we have some records that go back, in some cases, hundreds of years, but we're stuck really in this epoch. That's it. That's all we have. We have a huge amount of information from the sun, but we just have the one sun. But there are lots and lots of stars. Who's this young lady here? So, hi. How many stars are there?
Billions and billions.
There are more than that. There are actually billions and billions of galaxies. And what are galaxies made of? There you go. There you go. I have to remind my colleague, John Stockey, who's a cosmologist up on campus, that galaxies actually are made up of stars, and that's how you see them. But anyways, okay, so there are many stars. And in fact, as an example, the Kepler mission, which many of you are familiar with, is a planet hunting mission, a very exciting planet hunting mission. But it actually does some useful things. And that is, it observes, or it did observe when it was in its primary field, about 150,000 stars, very much like the sun, for a period of about half a decade. Now, if you think about that, if you're looking for rare phenomena that might happen on a star, say a superflare, a flare that was 100,000 times bigger than any flare we've ever seen in the sun, that could have catastrophic effects for our civilization, you know, does that stuff happen? Well, we can't answer that by observing the sun, particularly if it has a superflare and wipes us all out. Then it's not very helpful. However, if you can observe hundreds of thousands of stars for long periods of time, you can build up a statistical picture about these rare events. And you'll see papers in the literature, primarily in Nature, about superflares on solar-type stars that try to address this whole issue of how common these rare events are. But you need these large stellar data sets to really approach those issues at all. Oh, I'm sorry, question. Oh, thank you. Yeah. This is a field I work in all the time, and I really should have said that more clearly. Yes, we can see stars at all stages of their evolution, and particularly solar-type stars when they're very, very young and when they're very old, when they evolve into red giant stars. And that helps us understand the context of the early solar system when planetary surfaces and atmospheres were developing and evolving, and also what will happen to our solar system in the future. Okay, so I just wanted to go over some phenomenology that's associated with activity because it really is a phenomenological kind of area. And so there are a whole bunch of things that we associate with stellar activity that ultimately track back to changes in surface magnetic fields. So one of the most obvious things would be star spots. These are analogous to sunspots, or, as we heard earlier from Gary, Earth spots, which I thought was absolutely fascinating. I was actually going to ask that question, but he mentioned it already. You know, are there Earth spots? I guess that's pretty interesting. So star spots are dark regions that occur on stars, just like on the sun. And they're areas where the magnetic field is very strong, strong enough to suppress the convective heat flow from the near surface layers and create a dark area. And these can be seen most readily in broadband photometry, where you observe either, if you're observing stars, you observe them as point sources, and you just record the light from that star. This is what Kepler does. And so you observe the light curve, and suddenly you see a dip in the light curve, and then it comes back up again. Oh, we found a planet. No, that's a star spot. And in fact, Kepler, bless its heart, focused primarily on low-activity sun-like stars, much like our own sun. Because when you go to higher activity stars, the star spots themselves begin to corrupt the time series, making it ever more difficult to detect the low amplitude and rather infrequent planetary transits. It just confuses the whole situation. So Kepler very nicely has observed this very large sample of very sun-like stars, which is one important context. But also through its guest investigator program, it's observed a lot of very active stars that have been intentionally thrown into the mix, not to look for planets, but for their own right as active objects. There's another technique called Doppler imaging, in which if you imagine you have a rotating star and you happen to be favorably positioned, so you're more or less in the equatorial plane of that star, and then you imagine the star has a big spot on it that rotates into the field of view. So when it rotates in the field of view, it'll be on that approaching limb, and the signature of that star spot will then be blue shifted by the Doppler effect and mapped onto, say, an absorption line profile. If you're looking at an iron 1 line, for example, in the visible spectrum of the star, the signature of that star spot, it's actually quite complicated, will be mapped onto the blue side of that line profile. And then, as the star rotates and carries that spot into the substellar point, that influence on the line profile will migrate through the line profile until finally the spot hits the receding limb of the star. And when its influence is on the red side of the line profile, then it disappears. So by modeling those line profiles, one can get a sense of the distribution of spots on the surface of the star. And if one is extremely clever and has very good instrumentation, one can also measure the polarization of, say, this iron 1 line to get a sense of what the magnetic fields in the spot are like. There's a technique called Zeeman Doppler imaging, which can reconstruct maps of the magnetic field strength on stars that are suitably oriented and rotating fast enough in order to deduce the organization of star spots on their surface. This is fabulous, because otherwise one would need telescopes with apertures of many kilometers in size to do the direct imaging of these spots. Another aspect of activity that's quite commonly observed are flares, particularly from dwarf M stars. They seem to like to flare a lot. We see a lot in the Kepler record, and I'll show you an example of that fairly soon. A historical tracer of activity, one that's been known the longest, are faint emission cores in very deep chromospheric absorption lines. Primarily the calcium H and K lines at around 4,000 angstroms in the solar spectrum, so that's in the blue part, violet part actually of the spectrum. But they're also the analogous magnesium to H and K lines at around 2,800 angstroms, which is below the atmospheric cutoff. So these must be observed by high-altitude balloons or by satellites. And then finally, there's the hydrogen Lyman alpha resonance line. And who can tell me what wavelength this line occurs at? Thank you. So it's around 1,200 angstroms in the far ultraviolet part of the spectrum. These three features here are formed in what's called the chromosphere, which is a layer right above the photosphere. It's about 10,000 degrees in temperature. And these three species are the dominant cooling agents in that layer of the atmosphere, so they're extremely important. But that's not the end of the story, because as you move higher in the solar atmosphere, yes, sir? Oh, good point.
Calcium, okay.
Calcium's a good start. Singly ionized. Yeah. So here's where I start my rant and rave on astronomical nomenclature, as my British friends call it. Yeah. Yeah. I mean, everything is like you have type 1 supernovae, type 2 supernovae, population 1 stars, population 2 stars, class 1 supergiants, class 2, class 5 dwarfs. It's just crazy. The nomenclature is impenetrable, and I'm deeply sorry for all of you who have to learn all of this. And I would try to change it, but you know, I tried to get Pluto restored as a planet. I failed. That's right. That's right. Yes. Yeah. Carl was very well schooled in his younger years. Okay, so above this 10,000 degree chromosphere, oh, I should mention, since there's a special place in my heart for the chromosphere because I did my thesis work mainly on calcium-2 and magnesium-2, a little bit on Lyman alpha. This is a region of the atmosphere where the dominant metals, which are calcium, well, magnesium, iron, and silicon, and also to some extent calcium, are all singly ionized. So the spectra you see from these layers are always the 2s. But Lyman alpha hydrogen, very interestingly, is partially ionized through this region. So you'll see a lot of atomic hydrogen emission, and particularly Lyman alpha. Now above the chromosphere is a much hotter layer called the corona. It's about 1,000,000 degrees in the sun. It can be much, much hotter in other stars. And from these regions, you get emissions in the far ultraviolet, which is down around Lyman alpha, around 1,200 angstroms. In the extreme ultraviolet, which is down below the Lyman limit, cut off around 900 angstroms. And in the X-ray region, which is down at a few angstroms. The emissions that form at these temperatures, the emissions that one observes at these wavelengths form in a temperature range from about 100,000 degrees to many millions of degrees. And there are fabulous diagnostics in the X-ray region of these very hot temperatures, and in the far ultraviolet of these more intermediate temperatures. There are also phenomena that are associated with accelerated particles. For example, they're non-thermal radio emissions, synchrotron emission, gyrosynchrotron emission. They come from populations of accelerated particles. These particles are accelerated magnetic, typically in flares, in magnetic reconnection events, to extremely high energies, basically relativistic energies. They spiral around magnetic fields and release radio waves in the process. And these non-thermal radio emissions are signatures of accelerated particles, and therefore of these processes are associated with magnetic fields. So it's another symptom of stellar activity. And then there's the whole issue of winds. And our sun has a coronal wind, a 1,000,000-degree wind, that emanates from open field regions on the solar surface. And it's believed, I mean, it has to be true that the acceleration of the wind is intimately associated with the magnetic field. And so I would consider the stellar wind to be a property of activity. And we'll also see that it plays a very important role in the evolution of activity. Yes, I'm sorry. Yes.
They've been able to resolve stars
Yes.
and create maps where we can see dark patches moving around.
Yes, I mean, that's what I was saying. And that's basically a kilometer or more baseline. You would need equivalent. But to get the signal to noise and to actually resolve things, patches on the surface with high spatial resolution would require even more enormous telescopes, and probably a filled aperture telescope instead of an interferometric ray. But you're correct. I mean, interferometry is another technique that one can use to bypass the horrendous cost of these giant telescopes. Okay, so where does activity occur in the HR diagram? This is a fundamental observational question. And ignore the pineapples for the moment. But so this is the Hertzsprung-Russell diagram, and for some reason astronomers always plot these things backwards. But so low temperatures or low surface temperatures of stars are down here, and high temperatures are up here. Luminosity goes in the correct direction. So very high luminosity stars are up in this corner, and the low luminosity objects are down here. These are all faint red dwarfs like Proxima Centauri. The nearest star, about a parsec away, and it's 10th magnitude, which is really pathetic. It doesn't even make the Bright Star catalog. For goodness sakes, it's the closest star. And then up in this corner, you have the blue dwarfs and blue supergiants over here, which are extremely luminous, millions of times more luminous than the sun. But these are all hot stars over here, and they don't have surface convection. And as we heard before, convection is a very essential ingredient to the dynamo generation of magnetic fields. It's the powerhouse that provides the energy to create these fields. And then there's some catalytic influence due to stellar rotation. But without convection, you won't have magnetic fields. And so primarily we see magnetic fields just on this right-hand side of the HR diagram, where all the cool stars that exhibit surface convection fall. And if we look in detail at the solar surface as an example of what these magnetic fields can do, well, it's just a mess. I got to tell you, it's just a mess. So you have the photosphere here with the nice granulation pattern, but then emerging from that photosphere are these fibril-like magnetic fields that expand out into the overlying chromospheric layers. And this height scale here, well, you can see it here, it's in megameters, which is 1,000 kilometers. So height 0 here is sort of the visible photosphere. And then above that, around 500 kilometers, there's this transition into the chromosphere that I mentioned before. So this is all photosphere down here, and then there's this chromosphere. And then eventually you get up into these hotter layers at a few thousand kilometers above the surface. But down here in the photosphere, the magnetic fields are fibril and they're intermittent. They're just interspersed here and there. But once you get up into the outer atmosphere, the magnetic force lines have bloomed out, and they're all interconnected into this sort of canopy region up here, where there's a lot of activity. Now, down in the photosphere, the plasma beta is such that the field lines are basically frozen into the plasma. It's a high beta environment, and in other words, the gas pressure exceeds the magnetic pressure, and the magnetic fibrils are pushed around by the convective flow patterns in the surface layers, and that pushing creates a shaking and twisting the magnetic field lines, which manifests itself as Alfvén waves that travel up the magnetic fields, and also reconnection of the field line, which leads to atmospheric heating. So the presence of the magnetic field and the forcing of the magnetic field in the photosphere creates a lot of chaos up here in the chromosphere and in the overlying corona. And it's this complexity, which Phil Judge and I like to call the magnetic complexity zone, that leads to a lot of the observable effects that I wanted to mention. Oh, okay, I thought I'd show a couple of movies. This is a time series of a Kepler star. This happens to be a solar-like dwarf, much like the sun, but with a rotation period of only 1.6 days. And you see it has this nice modulation due to spots. Here's one with a slightly longer rotation period. Notice it has bigger spots. See these little blips here? You can tell me, oh, wow, it's a big one. What are those? Superflares. These are big, big flares. Look, this scale is 5% here. These are like several percent excursions. These flares here are 5% effects. It's extremely difficult to observe white light flares on the sun in integrated light. And only in the last few years have the irradiance people at LASP, Tom Woods and Greg Kopp in particular, been able to detect in their very, very high precision measurements evidence for solar flares in white light. But on these stars, they're huge. These flares are 10,000 times bigger than the largest flare ever recorded on the sun. So that's this whole superflare phenomenon. But you see that the light curves are changing all the time, and it's due to the varying spot patterns on these stars. And Kepler has been a huge mother lode of information on these activity diagnostics. So here, I just want to talk a little bit about calcium chromospheric emission. Here are the H and K lines in the solar spectrum. This kind of compressed view, and you see all these absorption lines in the solar spectrum, but then these humongous absorption dips that are due to these very, very strong resonance lines of ionized calcium in the solar spectrum, around 4,000 angstroms. Now, if you focus your attention, which you can't actually see here, at the very bottoms of these lines, this is a reproduction of what you see at the very bottoms of these lines. There's this little kind of double dip here, sort of an M-shaped thing. And these little emission features here are from the chromosphere. But they're at the very bottoms of these lines. So it's not a big effect in the calcium lines. And these are some of the Kepler stars with solar spectrum superimposed. So if you actually image the sun in calcium light, you see, well, the spots are dark, and most of the disk is sort of a neutral color. But you see these areas around the spots that are bright in calcium. Those are called plage, and they're regions of enhanced activity. But then you see away from the active regions, you see these kind of lacy network of calcium emission. That's called the supergranulation network, and that's present over the whole sun. And it's another sign of activity. It's more pervasive and more constant in time than the active regions, which come and go. But it's an essential part of activity. So these are the equivalent magnesium 2 H and K lines down at around 2,800 angstroms. And again, there are a pair of lines. And now you can't even see the photospheric wings very well of these lines because these features are so strong that they just basically blank out the whole photospheric emission. These These wings extend way off in that direction. But now you see that the emission cores are much brighter, and this is because the magnesium lines are much stronger than the ionized calcium lines, and it has to do with the fact that magnesium is more abundant in the solar atmosphere than calcium is. In fact, these lines are much brighter than Lyman alpha, which I'm going to show you in just a moment. So here is a part of the far ultraviolet spectrum of the sun, and I'm showing you a number of different stars here, but right here you can see the hydrogen resonance line, Lyman alpha, and ignore the little spikes here. These are all Hubble Space Telescope imaging, STIS, observations. These little spikes are geochronal emission from the Earth's geochronal, so just ignore them. But these big, broad features are the stellar emission lines, and they're deep absorption features in the centers of these lines, mainly due to the intervening interstellar medium. So the stars themselves, we start up at the top. We have an F-type subgiant, fairly solar-like, Alpha CMI or Procyon, and that's in the blue up here. And the observations are the jagged black lines, and the photometric errors are at the bottom of the blue envelope. So if you see a lot of color, that means a very high signal to noise. The sort of light yellow one here is the one of most interest. That's Alpha Centauri A, which is a solar-type star. And then there's Beta Geminorum, which is a K giant. It's got another big Lyman alpha feature. And then over here in this sort of pinkish color is Alpha Aquarii, which is a G2 star, just like the sun, but it's a supergiant. So it's a much more bloated kind of object. And then down at the bottom here is the M supergiant Alpha Orionis, or Betelgeuse. And it's actually showing nothing here. This is basically the noise level, but it'll become more interesting later. Now, probably some of you are thinking that there really is more to the spectrum than this. And in fact, there is. This is a movie, as a matter of fact. But let me just point out that there's a strong silicon-3 line. So the point here is that the whole far ultraviolet spectrum is just full, chock full of diagnostics of activity, all these high-temperature lines. So here's twice ionized silicon, silicon-3, and you see it's a very bright line in the spectrum. Oh, this is a heavily logarithmic axis, by the way. And you see this dip here. Kind of hard to see, but there's an absorption here on the blue side of the silicon-3 line, and that's due to a wind from Alpha Aquarii at around 40,000 degrees temperature. These two nitrogen-5 lines here, that's from 4 times ionized nitrogen, are formed around 200,000 degrees in this sort of intermediate zone between the chromosphere and the corona. So they're the hottest lines that are visible in this part of the spectrum. And well, you see the emission line, and that's where the activity is. And the wind is actually another manifestation of the activity, but it produces an absorption in the wind. Okay, so moving right along, so around 1250 here, you see this forest of carbon-1 lines, which actually are very little interest. That's why the movie's moving faster. And around 1300 angstroms, there's a triplet of atomic oxygen, which are very, very bright lines in the solar spectrum, extremely important. They show a lot of wind absorption in the more active objects. Then you have these carbon-2 lines, or the pair of carbon-2 lines here around 1335 angstroms. These are formed in the hotter layers of the chromosphere, and these are one of the prime diagnostics in the new Ayres solar facility, which Carl's group recently launched, a couple years ago, actually. And here you see the silicon-4 line, which is another feature that's captured in the Ayres bandpass. It's formed around 80,000 degrees, again in the subcoronal zone. So it's a very important line because it can be captured by STIS, by Space Telescope. And then there are these semi-forbidden lines of oxygen that sit around the weaker component of silicon-4. These are density sensitive. And when you go down the supergiant, you see these particular lines get much stronger. So you can tell something about the physical properties of the stellar atmosphere from these density sensitive features. And this movie marches along and marches along, and eventually it gets out to around 1,550 angstroms, where an important feature lies, or a pair of features, and that's the, by the way, here in Betelgeuse, you see these huge absorptions that are all broken up. Another one there. Those are due to carbon monoxide molecules in the exosphere, in the circumstellar envelope of Betelgeuse, that are absorbing out the ultraviolet light. So anyways, whoops, there goes the carbon-4 doublet. That's formed at about 100,000 degrees. It's an important signature of stellar atmosphere. Another important signature are X-rays, of course. Oh, I'm sorry, the question? Yeah, they all have a broad emission feature. That's Lyman alpha. They have a broad emission feature and a central absorption. And some of them had a little spike in the middle. That spike is unrelated to the star. It's an instrumental effect. It has to do with the fact that HST or Hubble is in low Earth orbit and it has to look out to the Earth's geocorona, in which Lyman alpha is emitting. And so you get this narrow Lyman alpha feature, and that's very common in these spectra. Yeah. So here's, you've probably all seen these kind of pictures before. I think it adorns the cover of this of the summer school. But anyways, these are Yoko X-ray observations of the sun near maximum and near minimum, where near minimum you see hardly anything on the solar disk, but at maximum you see all these bright active regions. So it's another manifestation of activity at much higher temperatures. Well, here's another movie I wanted to show about stellar X-rays, and this has to do with the Alpha Centauri stars that I mentioned before. So there are two stars. It's a triple system, but one of the stars, Proxima, is quite far from the main pair. These two are separated on the sky by about 20 arc seconds. So this is an arc second scale. So this is right ascension and declination in arc seconds. And so these stars are actually pretty close together. And in around 1995, they were about 20 arc seconds apart. And so what you'll see in this movie is a progression of these two symbols, one referring to the G2 star, the solar-like star, and the other referring to its companion, which is a smaller, less luminous orange dwarf, a K-type dwarf. But it turns out to be more X-ray active than its brighter, more solar-like companion. Now, the size of the dots is proportional to the X-ray emission from these stars. And when you just see the colored dots, that is predicted from a model of their cycles. But when you see a dark splotch, those are actual observations. So I'll try to run this movie. And so there are some observations back in the 90s from the Roentgen satellite, the German X-ray satellite. And there are a couple of periods when for a whole month these stars were observed. And you see their progression across the sky. Oh, that's Chandra right there, those two smaller dots. Oops, that's XMMNewton. It's less resolution than Chandra. And you see the solar-type star kind of disappears there for a while. Oh, here's Chandra again. And in the time since about 2005, Chandra has been observing these two stars about every 6 months. And you can see the kind of progression. Now you can see the orbital motion of these two stars around each other. And they're actually going towards a close approach in 2016. Now, when you watch these dots, you see like a little wobble. Can somebody tell me what that is? Parallax. Yeah, so Chandra has a high enough precision to be able to measure the parallax of the Alpha Centauri stars. It's less than an arc second. It's very impressive.
So these dots are much smaller now.
The resolution of Chandra, so there was a period there where XMMNewton was observing these two stars. XMMNewton could barely separate them because its resolution is much worse than Chandra. And that's why, and so Alpha Centauri apparently disappeared in the XMMNewton observations. And that's why we started the program with Chandra, because we were really concerned that, and for reasons that I could get into, that the solar-like star had suddenly dropped a factor of 50 in its X-ray emission. It turned out to be an instrumental artifact. I don't think I'll get to that part of the talk. But in any event, I just wanted to mention a little bit about energy balance in these different layers of the atmosphere, because this is actually rather critical to interpretations. So we have the photosphere of the sun. It puts out about 6 times 10 to the 10th ergs per square centimeter per second. And we'll call that 1. So on that scale of 1, the chromosphere is down here at 0.05. So it's not very powerful, is it? However, it's from this chromosphere and from these other layers, which are even more pathetic in some sense, that all of this high energy radiation arises that so influences the heliosphere. So just keep in mind that we're talking about a very, very small amount of energy, but with large import. We can do the same thing in terms of the masses of these layers. So the photosphere is pretty much up there. These are metric tons. 4 times 10 to the 17 sounds like a lot, but it's only a few times 10 to the minus 10 of the whole solar mass. So it's just a tiny, thin layer where all the visible light emerges. But the chromosphere, even compared to the photosphere, is 0.5%. And the corona is much, much below that, and the CME is really low. So who can tell me if there's something in the solar system that might have a mass comparable to the chromosphere? Just like some object or some part of an object in the solar system. And mind you, there are a lot of us that spend a huge amount of time studying all this fabulous phenomenon in this huge, vast chromosphere on the sun that's doing all these crazy things all the time. Enceladus? Oh, that's probably good. I don't know how much Enceladus weighs.
So this is
No, Jupiter.
This
Okay.
is half a mass of 0.5% of the solar mass?
No. The photosphere is a tiny, tiny fraction of the solar mass, and this is 0.5% of that tiny fraction. So we had to guess Jupiter. No.
So it's 10 to the 18 kilograms.
Something like that.
Right.
Yeah, isn't that amazing? Well, it turns out the mass of the chromosphere is very comparable to the mass of the Earth's atmosphere. Just to put that in perspective, the Earth is tiny compared to the sun. Now, here's the CME. We get worried about, remember that early slide where that CME was slamming into the Earth and creating all kinds of havoc? You know what the mass of a CME is like? How many of you were up at Bear Lake the other day? Now, there you go. Bear Lake. So when you hear, sorry Dan, but when you hear all these fabulous press, there's 100 billion tons of material is flowing out to the Earth and it's going to catastrophically roast us all, which it probably will someday. But in any event, the amount of mass that's actually involved in these CMEs is quite small, but their consequences can be very large.
The military always say it's not 1,000 aircraft carriers,
There you go. Well, of course, the speed and the temperature make a big difference. Now, if we go to stars that are more active than the sun, we find the picture changes. For these most active stars, the chromosphere gets to be about 15 times the strength of the chromosphere on the sun, which is not that much more. But when you go to the other atmospheric layers, you see a much bigger gain in power. And in fact, in these very most active stars, the radiative output or the energy output of the corona is very similar to that of the chromosphere. So these are real activity powerhouses because all of this coronal energy is coming out primarily in very hard energies, in X-rays, gamma rays, and that sort of thing. And it's this energy output that must equal the amount of heating that's going on, because it's the photons that are the only way of really carrying away that energy effectively. So this tells us that there must be a huge amount of magnetic heating going on in these stars. Okay, well, I don't want to spend a lot of time on this, but just to mention that if you observe a lot of stars and you measure their X-ray emission and you divide it by the bolometric flux of the star to create sort of a energy conversion or efficiency factor, and you compare X-rays to, say, carbon-4, which is that 100,000 degree diagnostic, you find that they're pretty good correlations. But that the power law that describes that correlation is steeper than unity. It's about 1.5. And that's just simply an expression, and it's even steeper here if you look at carbon, well, it's about the same if you look at carbon-4 versus this chromospheric magnesium-2 that I mentioned. You get this good correlation with the power law, but it's steeper than unity. If you put that all together, the X-rays versus chromospheric magnesium-2 would have an even steeper power law. And it's just a reflection of that more prodigious coronal output with increasing activity that I mentioned before. So here, this diagram right here, this kind of innocent-looking diagram by Andy Szymanich in a one-page paper in FJ Letters back in 1972 is the most quoted diagram in astrophysics, I believe, at least in my field. So you probably can't read all this, but what Andy Szymanich showed was that this is a time scale on the bottom in age in gigayears, and the sun is up here somewhere. And these are very young stars here. And what he found was that, or what he proposed was that the rotation of these stars decreases systematically with age, and that the calcium emission does as well. And this became known as the Szymanich law. The calcium emission decays with rotation roughly as the 1/2 power. And what this tells us is that the magnetic activity evolves with age, and what we understand now is that that's due mainly to magnetic braking by the coronal wind. I won't go into that much more. And then so this gets us into the whole area of stellar winds. And one thing I want you to take away from this is this diagram here, where I plotted the rotational velocity of stars versus their age. And so these are very young stars down here and older stars here. And these are based on observations from clusters that of known age. So Alpha Persei and the Pleiades are pretty young clusters. Hyades is a little bit older. And what you see in the very young clusters is the stars are all rotating pretty rapidly, but there's a wide range of rotation rates at these younger ages. But as you go down to older and older clusters, that rotational distribution kind of funnels down into a single one. And this is a manifestation of the negative feedback of coronal winds on stellar surface activity. So the faster a star rotates, the faster it spins down. The slower a star rotates, the slower it spins down. So there's this convergence or funneling effect. So by the time you get to Hyades age, all the stars are rotating about the same rate. And so the stellar winds, which mediate this whole phenomenon, are extremely important, but are extremely difficult to measure because these winds are extremely tenuous. They're very hot. The emission from these winds is almost negligible. The absorption, again, is almost negligible. The only way you can measure them is their influence basically on the local interstellar medium, where the winds collide with the interstellar gas and build up basically a hydrogen wall, which we can then see absorption effects from. And I'm running out of time, so I won't go into this. But if you read some of Brian Wood's papers, you can learn about this way of this asterospheric way of determining properties of stellar winds. So to kind of summarize Brian's work, he found that if you, and this measurement can only be done by done for certain stars that are well located with respect to the interstellar medium and their velocity through the interstellar medium, and with respect to us as well. So only a few stars were accessible by this technique, but what he found was that the mass loss per unit surface area seems to go up more or less as a power law with the surface flux of X-rays, or the X-ray luminosity, until you hit this wall here where it seems that the stars more active than that have very low mass loss rates. There's been some more recent work by Jeremy Drake and by Rachel Austin and Scott Volk that have also come up. They looked at energy and kinetic energy scaling arguments for coronal mass ejection, scaling from the sun and extrapolating to these stars. They also found power laws that show that the mass loss rate is proportional to the activity as parameterized by this X-ray index. So the stellar wind is very important. It's antagonistic to stellar activity in the sense that a star begins its life rapidly rotating, having gained angular momentum from the natal disk, but then almost immediately the coronal wind begins removing angular momentum, and then the star starts spinning down over its life. Now, it's one very interesting aspect to that. If you imagine you have two solar-type stars that are born in a close orbit, maybe a one-day orbit, they both will be tidally synchronized. So they will have a one-day rotation period. Now, as I said before, rotation is very important in this whole scheme of things. The faster a star rotates, the more coronally productive it is, and presumably the stronger the coronal wind, although one has to be a little bit careful because Brian Wood has some contradictory observations. But nevertheless, these stars are tidally synchronized, which means the rotation and the orbit are synchronized, but they're losing angular momentum due to the wind. And so that tries to detorque the spin rates of these stars, but the orbital tides, or the tides between the stars, will then extract angular momentum from the orbit to try to keep the spins in matched to the orbital motion. And that means as you're removing angular momentum from the system, you're removing orbital angular momentum. So what happens? Big crunch. And then so suddenly you have two solar-like stars that are happily minding their own business, and they're getting closer and closer together, and then they merge and they form a two solar mass star, which is completely out of equilibrium with itself, but spinning extremely rapidly. It turns into a giant star. And there are a few examples. These are called FK Comey-Berenice stars. Yes? Yeah. I can do 2 more hours if you like. Sorry. Yeah, I mean, I can do 2 more minutes. How's that? Okay. So, I just want to mention briefly stellar cycles, and it's going to be even more brief than before. So I think you probably learned a little bit about the solar cycle and how we explore it back in time. Cycles have been inferred in other stars by measurements of these calcium H&K lines, which are accessible from the ground. And here's a record of calcium intensity, and this is actually of the sun itself, measured by the solar stellar spectrograph at Flagstaff at Lowell Observatory, which can observe the sun through the same instrumental configuration as it observes stars. And here are some photometric measurements of the sun over the same period of time using more or less the same broadband photometric techniques. And you see when the sun is most active in calcium K, it is also brighter in broadband luminosity, which is a little bit counterintuitive because when the sun's most active, that's when all the spots are on the surface. However, it turns out those bright plages that I mentioned before overwhelm the stars in their extra brightness and make the sun a little bit brighter when there are a lot of spots on the surface and a little bit dimmer when there are no spots. And here's another star, HD telephone book number, and you see it has a cycle very similar to the sun's, and it also has this positive correlation between calcium brightness and photometric brightness. And I mentioned Sally Ballounis here, who has been really instrumental in carrying on a lot of this work from Owen Wilson's survey many years ago. And so here's a montage of other stars, and you see that there are some stars that are just flat activity, as if they were in a Maunder minimum. There are other stars that show peaks and cycles. This one down here is there's a nice cycle there. So there's a lot of sort of cyclical, non-cyclical, long-term behavior of these stars. And all of these black dots are stars that show long-term calcium modulations, whether they be cycles or just erratic variations. And you see, here's the chromospheric emission strength. And so these stars that are cycling are typically stars that are more active. And down at the bottom of the diagram, there are all these empty circles, and these are ones that are not variable. And some of these are solar-type stars, and some of these are more evolved stars that have slowed down their rotation and have become more inactive. Here's a diagram comparing some of these properties, like the photometric variations versus chromospheric activity. I'll call attention to that one. That's right here. So that's a cyclic photometric variation. And remember, in the sun, the luminosity of the sun gets a little bit bigger when it's more active, and that's these open circles here. So you see that there are a number of stars that seem to obey that behavior. But as you go to the more active stars, the dark spots seem to dominate the photometric behavior. So these are stars whose luminosity goes down when they're more active. So the darker spots are governing the picture. But in all these diagrams, you see the sun is just right in the middle. So it's not extraordinarily different in the bigger scheme of things. Well, I was going to talk about Alpha Centauri. And here are those observations. Well, we won't go into that. I'll skip the X-ray spectra. But I'll just show you the cycle. So there was this big problem back in about 10 years ago that in XMMNewton, the solar-type star in Alpha Centauri just completely disappeared from sight. It dropped a factor of 50 in its X-ray count rate. And this was very surprising to those of us who study solar and stellar cycles because it's completely unprecedented behavior. And it was really cause for concern because we had no explanation. It turned out it was an instrumental problem that XMMNewton is really sensitive only to the hardest X-rays from these stellar coronae. And these two stars, Alpha Centauri and B, are very solar-like, and they have very, what we call soft coronae, not very high energy coronae. So it was basically just that XMMNewton was kind of missing the bulk of the coronal energy distribution because it was only sensitive to the very hottest temperatures. But in any event, so this gray area here in the error bars, that's the solar cycle over cycle 23 and now cycle 24 over this time span here. And this hatched area is the projection of this 3-cycle average, which is the shaded area, into the future. And you can see cycle 24 in the sun has been kind of disappointing in terms of the projections. And people were thinking down around this time that we're going to go into a Maunder minimum. This curve here is for Alpha Centauri, the sun-like star. And you see it was high back in the 1990s when it was observed by Rosat and then by Chandra. But then it was really low here during this period. I left off the XMM observations because they have this instrumental effect. And it stayed low for a long time. And then it's only just recently started to come up again. So this is kind of like a mini Maunder minimum. But look at Alpha Centauri B. It's been extremely reliably cycling in X-rays. Now, the interesting thing about this is that the amplitudes here are orders of magnitude larger than what we see in calcium H and K. So the X-ray cycles of stars are huge compared to their calcium cycles. And this is just a summary of that part, but I'll leave it there because I'm way out of time.